Okay, now we're going to go over the significant zeros. POCL, remember pause and fast forward is needed before you get to, make sure you check all your work before you get to the practice questions. So it says when working with measurements, it is important to know which digits in the measurement are significant, which ones are not. Non-zero digits are always significant. That's probably important, so that's something I should probably highlight. So non-zeros are always significant. They always count. However, zeros can be tricky. Some are significant, others are not. This activity will help you learn the rules for determining whether a zero digit is significant or not. So if it's just a regular number, 1, 2, 3, 4, 5, 6, 7, those are always significant, but zeros are sometimes significant, sometimes not. Okay, so the first one, it says, for each balance in Model 1, circle the phrase below that best describes how closely the mass can be determined with that balance. So if we look at the balances, it's asking for the Econo balance, a good balance, balance pro, and exacto balance. So if you look at sample A or B, the Econo balance is measuring this rock at 100 grams, but this balance, the same rock, is measuring it at 140 grams. This one's measuring at 143, and this one's measuring at 143.0. So you should notice something about the decimal places. So it seems that the Econo balance is only estimated to the nearest 100 grams. Fix this. Because it's reading this, the same rock at 100, this one's estimating at 140. So this one's only doing it to the hundreds place. To every 100 grams, I'm sorry, not hundreds place. The good balance is a decimal over. So instead of 100, it's measuring at 140. So this one is estimated to the nearest 10 grams. The Balance Pro, not only is it picking up 140, but it's picking up a 3. So this one's more precise. So it's picking it up onto the ones place. So estimated to the nearest 1 gram for this one. And for this one, it picked up a 0. So this is the tenths place, or the nearest 0.1 grams. So that's what they're estimating at. For number 2, it says, which of the 4 balances in Model 1 is the best quality instrument? Well, you know, the more precise something is, the more quality it has. So the Exacto balance is probably the best one because it can estimate to the nearest tenths place. Number 3, rock C is placed on the Econo balance and the balance reads at 200. So this is probably important. So it reads at 200. Does rock C have a mass larger, smaller, or the same as sample A, or is it impossible to tell? Explain your reasoning. So let's look at sample A again. So sample A is measuring at about 100 to 143 grams. So rock C is going to be larger because 200 grams is bigger than 100 to 143. So for B, does rock C have a mass larger or smaller or the same as rock B, or is it impossible to tell? Let's go look at B. For sample B, it's between 200 and 177.1 grams. So for this one, it's impossible to tell. The Econo balance doesn't give enough information, even though the reading for the 2 rocks are the same. The measurement is estimated, so one might be larger than the other. So this one is impossible to tell. Okay, number 4. The mass of rock C is then measured using the other 3 balances. The results are shown below. So the Econo balance read 200, Balance Pro read 177, Good balance read 180, and Exacto balance read 177.0. So A, based on this additional information, does rock C have a larger mass, smaller mass, or same as rock B? Is it impossible to tell? Explain your reasoning. So it looks like between the 2 best quality ones, the Balance Pro and the Exacto balance, This one's reading at 177. This one's reading at 177.0. So it looks like rock B has a greater mass by 0.1 grams. But the last digit in the measurement is uncertain. So I guess you can say, because this is always a guesstimation, that it's impossible to tell since this is an estimated digit. Okay, for B, explain why the 0 in the exacto balance reading provides provides important information about the mass of rock C, but the 0 in the good balance reading does not. So exacto balance here provides important information, and the good balance does not. So the 0 in the good balance reading is neither certain or uncertain, because the estimated number is an 8, and it serves as a placeholder. But the 0 in the exacto balance is the uncertain digit, so it gives important information. So this one has, it's more specific compared to the good balance. So this one gives more important information than this one. Okay, number 5 using model 2. So it says, for each balance in model 2, write a phrase to describe how closely the mass of an object can be determined using that balance. The first one is done for you. So it says the balance pro is estimated to the nearest 1 gram. So you can see that because it's only in the ones position in both of them. So now you have to finish the sentences for the other ones. So for this one, for the centi balance, it's at 0.012. So you can say that it's estimated to the nearest 0.01 grams or the hundredths place, either one. And then the super balance is reading 0.016. So you can say that it's estimated to the nearest 0.001 grams or the thousandths place. For number 6, Pebble A and Pebble B both have a mass of 0 on the balance pro in model 2. Do these pebbles really have no mass? If no, explain why the balance is reading 0. Okay. So it seems like their mass is probably less than 1 gram. But the balance is not sensitive enough to give a reading. So it's probably, well, it has to be more than 0.0. But it's just that it's not as precise as the super balance, so it wouldn't be able to give you an appropriate reading. Which balance is sensitive enough to determine if Pebble A has a larger or smaller mass than Pebble B? So let's look at this one, Pebble A and Pebble B. So this one's reading at 2, so these read the same. These two are also reading the same. So it looks like the super balance is the only one that shows any difference in mass. So this one's reading 20 grams and this one's reading 16. So that's the only one that's sensitive enough to make the reading. Okay, number 8. The mass of reading Pebble B in the super balance is 0.020 grams. This value is very close, but different than the mass reading for Pebble A on the same balance. Determine which of the 3 zeros in the mass reading for Pebble B is the most significant in terms of determining whether Pebble B has a different mass than Pebble A, and circle the 0 below. So let's look at the balances. It's asking for the most significant number to determine the weight. So if we look at the super balance, here it's reading at 1.16 and this one's reading at 0.020. So you can tell that this one is, the 0.20 grams is bigger, but the most significant digit is probably this one at the end, because this super balance is reading up to the thousandths place. So the most significant number in this one is probably the 0 at the end, because this is giving us the most precise reading. And it's something that the balance can pick up. Okay, Model 3, types of zeros. So Model 3 shows several of the measurements from Model 1 and 2. The zeros in those measurements are categorized in 2 types. List the 2 types. So it's giving you a bunch of different zeros, and then here it says that these first two are placeholder zeros, and these are significant zeros. So the two types would be placeholder zeros and significant zeros. For number 10, consider the phrase placeholder as it is used in the English language. Discuss two examples of this term in your group and summarize them here. I mean, there could be several answers for this question. You can say a placeholder could be related to someone holding a place in line, or using a bookmarker to hold a place while you read, or placing your coat somewhere to save a seat. Anything that determines a placeholder. Number 11. Describe the two types of placeholder zeros that are shown in Model 3. So if we look at the placeholder zeros, right here, it looks like there's zeros either before an implied decimal. So this is 200 grams, but you would tell yourself that there's a decimal at the end. And there's also zeros after decimals. So 0.02. Those are considered the two placeholders. So number 12, if you remove a placeholder 0 from a number, would the numeric value of the number change? Yeah. So for example, if we get this 200 and we took away these two zeros, then we would be left with 2. And that would be a significant difference between 2 and 200. So you would completely change the value of that number. So 13, describe the location of significant zeros in a number relative to the decimal point. So let's look at the decimals. So here's the decimal right here. So if you look at it, they're always to the right of a decimal point and also at the end. So to the right, to the right, to the right, and then zeros at the end. So those are the two situations. Let's look at the next number. Number 14. If you removed a significant zero from the end of a number, would the numeric value of the number change? Let's look at an example. So like this one. The value for the end of the significant figure, it wouldn't change. Like let's say we were to get rid of this zero right here. It would go from 177.0 grams to 177 grams, but the value of the number is still the same. Okay, number 15. Determine if the zeros in the measurement below are significant or not. If a zero is significant, underline it. So if we look at this first measurement, 650 meters, this zero is actually not significant. There's no decimal point, so this is an implied decimal point. So whenever there's an implied decimal point, the zero is not significant. For this one, however, it does have a decimal point. So this one is significant right here. So 42.0 seconds. That one does count. There's a decimal point here, so you know that they placed it there for a reason, and it's to estimate to the next place. For this one, again, it's an implied decimal. So for this one, these zeros are not significant. So in this number, you would have two significant figures. So the 6 and the 5, the 0 doesn't count. For B, you would have three significant figures, 4, 2, and the 0, because it's after a decimal point. It's to the right, like we just said in the other problems. And then this one, this would have one significant figure, because these are implied decimal points. For this one, all three of these would be significant, because again, it's after a decimal point. So this one would have 1, 2, 3, 4 significant figures. For this one, if it's at the beginning of a number, remember the decimal point has to be, the 0 has to be to the right of the decimal point in order for it to be significant. So for this one, there'd be no significant figures. So there'd be one significant figure, and it would be the 8, but these zeros, none of them would count. For this one, only this 0 would count because it's to the right of the decimal point. It's at the end of the number. So anything before the first significant figure isn't going to count. So this one would have 3 significant figures. For number 16, it's giving you the rules for significant digits, and this is just something you have to memorize for a test and stuff. So it says there are 5 rules for determining which digits in the measurement are significant. Match each rule to a set of examples in the table below. So the first one is all non-zero numbers are significant, which we talked about at the beginning. So if any number that's not a 0 always counts. Rule 2, sandwich zeros. Those that occur between 2 significant digits are significant. So if it's sandwiched between 2 significant figures, it does count. Zeros that are only placeholders for a decimal are not significant. So this one, 650 meters. This is a placeholder for the decimal so that we know that it's 650 instead of 65. So this one doesn't count because it's only a placeholder. Same thing for these and these. These are only placeholders to let you know that this eighth is in the thousands place, but that's their only purpose, so they're not significant. Exact numbers, zeros at the end of the number also contain a decimal are significant. So this is why this one is significant. These two in the front are just placeholders to let you know that the significant digits are in the thousands place, and then this one it does count because it's at the end of the number and it contains a decimal. Exact numbers, no doubt, or uncertainty in this value, may be thought of having an infinite number of significant digits. These include numbers that were counted in defined values or conversion factors. So that's talking about like scientific notation when it's like 4.2 times 10 to the 8th power. So number 17. In the measurements below, the significant digits are underlined to determine the rules that were used to decide which digits were significant and which ones were not. So if you look at A, you should have noticed that rules 1 and rules 4 determine the number of significant digits in this one. For B, it was rules 1 and 3. For C, it was rules 1 and 4. For D, it was rules 1 and 5. For E, it was a bunch of rules. It was 1, 2, and 4. And for F, it was rules 1, 2, and 3. For 18, underline all the significant digits in the following values. So for this one, let me get a liner. Only the 9 and the 4 count. Because remember, this is an implied decimal, so these are only placeholders and they don't count. This one, only the 7 and the 2 count. The other 2 are placeholders, so they don't count. This one, 4, 3, let me underline it correctly. 4, 3, 8, 0 are significant because the 0 at the end is at the end and there's a decimal point. This one, this one's to the right of a decimal point, and this is after the digit, so all 4 of these are significant. So 4, 0, 0.0, there's 4 significant figures in this one. For this one, there's an implied decimal point. So this 8, this 0, and this 5 are significant. This last 0 at the end is not because there's no decimal point. These 2 zeros are sandwiched between 2 significant figures, and that's why those are significant. For this one, there should only be one significant figure, which is the number 1. Because the other 3 zeros were placeholders. Okay, for Model 4, scientific notation, significant digits are underlined. So it's already telling you the number of significant digits in this one. For number 19, the measurements in Model 4 are written in both scientific notation and expanded notation. Copy one example of each below. So we can use the first example. So in scientific notation, this was written as 3.00 times 10 to the 4th meters. And in expanded notation, it's 30,000 meters. Says, do the 2 measurements have the same numeric value? Yeah, so 3, this is the same as this. They're equivalent to each other. were the two measurements made using the same instrument? No, the second instrument, 3.00 times 10 to the 4, has more significant digits. That's implying that it was made with a more sensitive instrument. So this one only has one significant digit. This one has 3 significant digits, so that's why you can tell that this one's more precise. It says, look at the measurements in Model 4. When a number is in scientific notation, it is changed to expanded notations. Are there any added zeros? Are any of the added zeros significant? Give 2 examples to support your answer. Let's see. Let's use the same one. So let's use 3.00 times 10 to the 4th power meters. And then that was equivalent to 30,000. Says, are any of the added zeros significant in expanded form? So there's actually less significant figures here. So no. The scientific notation has more significant figures than the expanded notation, so that's a no. I'm going to use a different example for number 22. Number 22, when a number in scientific notation contains a significant zero, is that zero also significant in expanded notation? Give examples to support your answer. So let's look at this one, 7.0. So it's 7.00 times 10 to the negative 3. I forgot what the units are. kg. That was equal to 0.00700 kg. So in this example, that's a yes, because this one has 1, 2, 3 significant digits here. Remember, these two are placeholders, so they don't count. And this one has 1, 2, 3 significant digits here. So for this one, it's a yes. For number 23, write each of the measurements below in expanded notation and underline the significant digits. So let me just do that real quick. There we go. So you guys should remember the rules for scientific notation. If you're moving the decimal to the right and you're making the number bigger, it's always a positive exponent. So this one made the number bigger, this one too. If you're moving the decimal to the left and you're making the number smaller, this is way smaller, then the exponent is negative. Remember that you always need units. Even on the practice problems you have today, if you're missing units, it'll count the entire answer wrong. Okay guys, so if you've checked all of your POGIL answers and you're all in agreement, you can start the practice problems on benchmark 1. That's due by 11:59 p.m. today. Alright, hope that helped. If you have any questions, come in for tutoring or email me.